Brought to you by Specialized Imaging. This video will serve as a condensed demonstration of 3D processing in the TEMA motion analysis software. The first step is to load both or all image sequences to be used for 3D. When loading each sequence, camera information must be detailed. Focal length and pixel size are typically required, so prior knowledge of the test is recommended. If a lens calibration has previously been completed, the Import Parameters button can be used to load the calibration file. There are multiple 3D calibration options available in TEMA. The first method is absolute orientation, where points in the scene are surveyed for X, Y, and Z values in a desired coordinate system. The values need to be loaded into TEMA by way of a text file as shown here. Once this file is loaded, a 3D visualization of the points is shown. The same points are then loaded for the remaining cameras. To properly place these points on each image, the user should have a reference available as seen here. Each point must be carefully placed on each image and adjusted to the best possible accuracy the user can achieve. The absolute camera orientation is then performed with the static camera calibration option using all points placed. If a lens calibration was not performed, TEMA offers an option to calibrate the focal length during this process. The results of the absolute orientation show the XYZ and roll, pitch, and yaw of the camera in the surveyed coordinate system, along with an adjusted focal length. Residual error measures for each calibration point are provided. If these numbers are acceptable, this calibration can be applied. This process is then repeated for the remaining cameras. Another calibration option, known as relative orientation, uses relative points with no known XYZ positions. To calibrate, only a single distance between any two points is required. Here, 10 points are added to each image and adjusted to the best accuracy possible. The relative orientation option is then chosen. The points to be used are chosen and the primary camera is selected. The primary camera will be the center of the coordinate system initially, and the system can then later be transformed to a more desirable origin and axis definition. The result of the relative orientation is the primary camera being zeroed and the remaining cameras being located relative to the primary. Parallax values are provided for each calibration point, and if these values are acceptable, the calibration can be applied. A 3D visualizer allows the user to see the result of this calibration for verification. Both cameras are now calibrated. Calibration points can now be disabled and the test is now ready for 3D tracking. The first point placed in this example is on the sled and is named sled. When a point is added to the other camera view and given the exact same name, an epipolar line appears to help with point placement, if needed. This line is a projection from the first camera, and if the point needed lies exactly on the line, this shows the calibration is correct. Both points can then be tracked through the image sequence. Two more points are added for this example to track the head and seat. The seat point in this example is tracked in one view using the quadrant symmetry algorithm and in the other view using the correlation plus algorithm. A point zoom can then be opened for each and the points are tracked through the entire sequence. Now Now there is 3D data for 3 points in this test. 3D position for the tracked points can be added to a text diagram spreadsheet and shown in the chosen coordinate system. A name can be given to the spreadsheet and the columns adjusted as needed. A 3D diagram can be created to show the movement of each point in 3D space, with the coordinate system shown for reference. This diagram can be manipulated in whatever way is needed. Camera visualizers can also be added for a better sense of orientation and setup. A multi-axis diagram can be used to display 4 different components for different points on the same plot, such as x, y, and z displacement, velocity, and acceleration. These components can be placed on any y-axis and their properties changed at any time. In this example, the x, y, and z positions for the head are shown along with the error volume for the head point. A 2D diagram can be made to display any component for 1 or more points: displacement, velocity, or acceleration in x, y, z, or absolute. In this example, y position for the head, seat, and sled are all shown. Velocity and acceleration can also be displayed in diagrams. Here, the x position, x velocity, and z acceleration for the head are all shown on the same plot, with the option for max and min y-axis values to be displayed. All parameters of interest can also be displayed in text diagram spreadsheets and exported as necessary. Here we see head position, seat position, and error volume for the sled. Because the error volume is low in this case, the error volume is swapped for sled velocity in the x direction. Distances and angles can be added for 3D, and x, y, and z components or absolute values can be obtained for every frame. "3D angles can also be measured in 2, 3, or 4 point. In this example, the angle between the head, seat, and sled is calculated. These values can be displayed in any diagram format and exported. Here we can see the x, y, and z components for the distance, the absolute value of the distance, and the angle all shown in the same text diagram spreadsheet. All of the windows inside of TEMA can be arranged in any manner, and their state will be maintained once saved and reopened. Diagrams, spreadsheets, and overlays are always synchronized with the image sequence.